In this lecture, we are going to discuss about the energy Eigen functions for the quantum harmonic oscillator. In the first lecture, we have already discussed about the properties of classical harmonic oscillators, and in the second lectures, we introduced that how to solve the Schrodinger equation for the quantum harmonic oscillator and to obtain the energy Eigen values. And in this lecture, we will deduce the expression for energy Eigen functions. So we have started from the Schrodinger equation, and we have at first started by assuming an asymptotic solution. For this, I request you to listen the previous lecture. So it was started from the Schrodinger equation. This was the Schrodinger equation, and then we started assuming some asymptotic solution. So these are the asymptotic solution. Then we assumed the nature of the exact solution, and with this value when substituted in the Schrodinger equation, then the Schrodinger equation became like this, that equation 4.79. Then we told that the value of lambda here, that is in this equation, will be 2n plus 1 for an acceptable solution. So if we put lambda is equal to 2n plus 1 in this equation, that is equation 4.79, so then this equation will become like this, that is d2 Eigen by dx square minus 2y d Eigen by dy plus 2n into Eigen is equal to 0. So after substitution of the value of lambda is equal to 2n plus 1, the value of lambda, why it should be 2n plus 1, was described in the earlier lecture. So if we substitute the value of lambda is equal to 2n plus 1, then the equation for the quantum harmonic oscillator, which was started from the Schrodinger equation, and after proper substitution of the solution, the equation is like this, that is 4.89. So this is the equation now, and we will discuss about the solution of the equation, and from there we will deduce the expression for the energy Eigen function of the quantum harmonic oscillator. So let us look carefully to the equation described by 4.89, and the solutions of this equation are actually Hermite polynomials Eigen of degree n. And for the details regarding the Hermite polynomials, I advise you to go through any standard mathematical physics textbook. Some important properties of the Hermite polynomials are, that is, there are some special recurrence relation. For example, Eigen prime is equal to 2n Hn minus 1 Hn plus 1, that can be expressed as 2 zeta Eigen. Zeta is actually H is a function of zeta. It may be x or maybe y, whatever it is. So Hn plus 1, that is higher order H values, can be expressed in terms of lower order H values. These are known as a recurrence relation. Another important formula is Rodriguez formula, that is Eigen zeta is equal to minus 1 to the power n e to the power zeta square dn by d zeta n and e to the power minus zeta square. So this is the Rodriguez formula through which we can determine different Hermite polynomials. So n is the subscript, and n stands for different values of the polynomials. For example, if you set n is equal to 0, then h0 zeta is equal to 1. I am again telling that is h is a function of zeta. In some books it is interpreted in terms of x or y. So h is a function of zeta, and for different values of n we will obtain different Hermite polynomials. For example, this is h0 zeta is equal to 1, H1 zeta is equal to 2 zeta, H2 zeta is equal to 4 zeta square minus 2. In this way, in this book, H5 zeta has been shown. So these are the different Hermite polynomials, and the orthogonality Eigen zeta and Hm zeta, that is written in terms of this equation, that is minus infinity to plus infinity e to the power minus zeta square Eigen zeta Hm zeta is equal to 0, n is not equal to m. So this relation is valid when n is not equal to m. For n equal to m, the same relation can be written in this way, that is minus infinity to plus infinity e to the power minus zeta square Eigen square zeta d zeta is equal to root pi 2 to the power n factorial. Here the derivation is not shown, but I advise to go through some standard textbooks where you can find the derivation of this particular orthogonality relation. However, in the present lecture, we will use these values, that is different values of the Hermite polynomials and this orthogonality relation. And for further description regarding the Hermite polynomials, we have to go through the textbook concerning the mathematical physics. So this equation is known as the Hermite's equation, and solution of this equation are known as Hermite polynomials Eigen y of degree n. So the energy Eigen function that can be represented as psi n y is equal to n Eigen y, n is a constant here, Eigen y e to the power minus y square by 2. I think in the previous lecture, I think you can remind that we assumed the solution like this. Here n is an extra, that is we have assumed some constant term, but the exact solution was the multiplication between a Hermite function and one exponential term, that is e to the power minus y square by 2. We have already discussed regarding the exact solution of the Schrodinger equation of the quantum harmonic oscillator. So that is written here only, nothing more than that, just one extra constant has been written n, and here y square is equal to m omega by h cut x square. It was already discussed in the earlier lecture. We have assumed some special dimensionless parameter, so y is such a parameter where y square is equal to m omega by h cut into x square. Now this is Eigen y. Now I have already shown you, that is different values of the Hermite polynomials for different values of n. So these are the different Hermite polynomials for different values of the n. Now what we have to do, we have to evaluate this constant term from the normalization condition. So from the normalization condition, we know how to normalize a particular wave function. So if you normalize this function, so you will obtain minus infinity to plus infinity, and this constant term has been taken outside of the integration, and the integral is Eigen square y e to the power minus y square dy is equal to 1. So this is the normalization condition. We know how to normalize a wave function. So from the normalization condition, the value of the integration will be root pi 2 to the power n factorial. Just earlier I have shown that we will use the normalization condition of the Hermite polynomials. So here we have used the result only. For detailed derivation, we have to go through some standard mathematical physics textbook. So here we have used the value of the integral for the normalization condition of the Hermite polynomials. So root pi 2 to the power n factorial is the value of the integration here. So from this equation, we can easily calculate the value of the constant n. So this is the value of the constant n described in equation 4.92. So we will put this value to this equation of the wave function, that is 4.90. This is the main equation of the energy Eigen function. So if we put the value, then the normalized eigenfunction will look like this. That is, this is the normalized eigenfunction that has been described by equation 4.93. This is the normalized eigenfunction. Now, if we put different values of n, then we will get different values of the eigenfunction corresponding to different state. For example, if we put n is equal to 0 here, so psi 0 will be, we have to put h0y, then value of the h0y is 1. So in this case, that h0y will be 1, and minus in place of minus y square by 2, they have written the value of the y given earlier. This is the value of y square is equal to m omega by h cut into x square. So it has been, y has been written in terms of x. That is why in the left hand side we are not writing y, we are writing x, because in the right hand side that y has been written in terms of x. So this is the expression for the psi 0 x. In this way you can evaluate different expression for the wave function for different states. For example, these are the expression for wave function for different states. This is for psi 1 x. Just what you have to do, you have to know the Hermite polynomial for n is equal to 1, and you have to substitute h1 x in the psi, in the expression of psi. In this way you can evaluate different wave function for different states by substituting the exact expression of the Hermite polynomial. So after finding the wave function psi nx, you can also calculate the probability density mod of psi nx whole square. We know that expression for the probability density is mod of psi nx square. Now, if we know the expression for psi nx and mod of psi nx square, then we can plot these wave functions for different states. So let us discuss about the plots. So at first look at this figure. So in this figure, the x-axis represents the displacement of the oscillator, and the y-axis represents both energy and wave function. You see that it has been written E comma psi x. So that represents, y-axis represents both energy as well as wave functions. Now why there is a parabola, this was already discussed in the previous lecture, but still I am mentioning that this parabola comes for the potential Vx, because Vx is equal to half kx square. So the potential and the displacement x, there is a relation of parabolic nature, because Vx is equal to half kx square. So from this relation we can ascertain that Vx will be parabolic in nature. So that Vx is represented by this parabola, and these horizontal lines, they represent the energy values for different states. For example, n is equal to 0, energy will be half h cut omega. Why? Because in the previous lecture we have deduced that energy E is equal to n plus half into h cut omega. So if we put different values of n in different states, you will obtain the energy values for the different states. So this horizontal line represents the total energy value for n is equal to 0. This value, that is 3 by 2 h cut omega, this is the total energy value for n equal to 1. This is the total energy value for n equal to 2, and so on. And for n equal to 0, we have obtained the wave function like this. So this is the expression for the wave function for n is equal to 0. Now we can plot it. So if we plot the wave function, so this will be like this nature. So you see that this curve is symmetric along the y-axis. So if you consider that y axis is a mirror, so this portion has a mirror image in the right hand side. So actually this type of graph is the nature of the even function. So if you see that the graph is symmetric along the y-axis, then we can say that this function is symmetric or even function. Now for n equal to 1, that is for the next state, if we plot, the wave function will look like this. But you see that this is not symmetric, because if you take a mirror image of this portion, so this portion should be in the upper half, but actually it is in lower half, so this is anti-symmetric. So this is a nature of the odd function. So if you carefully look different graphical nature at different states, so we can say that the wave functions are even or symmetric for even number of states, that is for n equal to 0 and for n equal to 2, n equal to 4, and so on. And the wave functions are antisymmetric or have or are odd function for odd states, that is for n equal to 1, n equal to 3, etc. Actually this is understandable from the expression of the wave function also. So what is the expression of the wave function? The expression for the wave function is e to the power minus y square by 2 multiplied by the Hermite polynomial Eigen y. Now the point is that e to the power minus y square by 2, this part is always even, because you see that there is minus y square in the numerator, so this should be even function. This is always even. Now Eigen y, that is the second part, Eigen y, that is even or odd according as n is even or odd. Why I am saying that? Because you see these are the expression for the polynomials. So if we look those expression, it is easy to understand that for odd states, for example h1 y is equal to 2y, so this is odd function. Even you see that is for h3y, so this is odd state. And if you see, look at the expression, so you can see that this is also the expression for odd function. But for even states, for example h0y, where n is equal to 0, that is even number, this is even function. For h2y, this expression is for even function. So as the Hermite polynomials are even function for even values of n, and Hermite polynomials are odd function for odd values of n, that is why we are obtaining the wave functions like this. That is, wave functions, nature of the wave function is even for even states, and wave functions are odd for odd states. It may also be noted that the quantum oscillator can be found outside the parabolic potential barrier, since psi does not vanish at the classical turning points. In other words, the particles can penetrate the barrier to some extent. The barrier penetration is an important feature of quantum mechanics. This is very important concept, and this behavior is different from the classical harmonic oscillator. So I am again discussing this fact. If you look at this graphical nature of the wave function, you see that this boundary, that is that boundary of the potential, we can consider that this is the classical potential barrier. Potential barrier means, when we have discussed about the classical harmonic oscillator, so there we have told that the oscillators can never be found outside this boundary, because this is the boundary of the potential of classical harmonic oscillator, and the classical oscillator cannot be found outside of this boundary defined by this parabolic curve. But when we are plotting the energy Eigen functions of the quantum harmonic oscillator, we can see that this part, for example, suppose you look at this part, so some portion of the energy Eigen function is outside the potential barrier. That means there is some barrier penetration. So this is an important feature of the quantum harmonic oscillator, which is different from the behavior of the classical harmonic oscillator. Even we can also see from the plot of the probability density. You see that mod of psi x whole square is the plot of the probability density, and if this is the plot of the psi n x, this is the plot of psi n square x for n equal to 0. So this is for n equal to 1, this is for n equal to 2, this is for n equal to 3, and so on. Even you see that probability density, this dotted curve describes the probability density, and it is also shown outside of the potential barrier. So it indicates that there is some barrier penetration, and this feature is essentially different from the behavior of the classical harmonic oscillator. Another interesting point to be noted in connection with the results is the nature of probability distribution of classical and quantum oscillators. Classically, the probability of finding the oscillator at a given point is inversely proportional to its velocity at that point. And in the beginning of the lecture regarding the quantum harmonic oscillator, we started from the discussion of classical harmonic oscillator, and there we told that the velocity of the classical harmonic oscillator is 0 at the boundaries, that is turning points, and there the direction of the velocity changes, and there the oscillators or the objects spends the maximum time, and the probability of finding the classical harmonic oscillator is maximum at the turning points and minimum at the position of equilibrium. And classically it can be shown that the probability of finding the oscillator at a given point is inversely proportional to its velocity at that point. The total energy, we know that for a classical oscillator is half mv square plus half kx square, or from this expression we can say that the velocity is equal to root over of 2e minus kx square by m, and therefore the classical probability, as it is inversely proportional to the velocity, this is the expression for the velocity. So the classical probability Pc, that should be proportional to the root over of m by 2e minus kx square. Now this probability is minimum at x is equal to 0, mean position, that is position of the equilibrium, and maximum at the extreme position, that is the probability of finding the oscillator at the turning points or the extreme position is maximum. In the quantum case, for n equal to 0, the probability is maximum at x is equal to 0, and as the quantum number increases, the maximum probability moves towards the extreme position. So let us look at the graph of the probability density again. So you see that this dotted curve is the quantum mechanical probability density for n is equal to 0. Now where is the peak? The peak is here, that is equilibrium position. So for n equal to 0, the probability of finding the particle is maximum at equilibrium position. So this is exactly opposite to the behavior of the classical harmonic oscillator, because for classical harmonic oscillator the probability of finding the particle at the equilibrium position is the minimum, and where it is maximum at the turning points or the extreme position, that is in this position. In this position this should be maximum. But you see that for n equal to 1, the value of the position of the maximum probability that shifts slightly, that is away from the mean position. This is the mean position. So maximum value shifts here, and in this side it shifts here. Again, you see that the plot for n equal to 2, you see again that the position for the maximum value, it is slowly approaching to the extreme position. You see the plot for n equal to 3, it is slowly approaching, the position of the maximum probability density is approaching towards the extreme position, that is where the probability for the classical harmonic oscillator is maximum. Now let us see a figure for probability density psi square for the state n is equal to 10. Now here two curves are shown. One is solid curve. This solid curve is for the quantum mechanical harmonic oscillator, and this dotted curve is for the classical harmonic oscillator. So you see that for n equal to 10, the maximum value of the quantum mechanical oscillator is very close to the maximum value of the classical harmonic oscillator. But still there is some discrepancy between the behavior of the quantum and classical oscillator, because the quantum mechanical is in quantum mechanical oscillator there is a very rapid oscillation for sin square, but for classical harmonic oscillator there is not so much rapid oscillation. Let us look at another figure for, you see that is it is for n equal to 20. So for n equal to 20, the maximum of the quantum mechanical oscillator is very close to the classical value. So as we increase the states n, so at that time the position of the classical probability and quantum mechanical probability approaches very close. So this is basically in agreement with the Bohr's correspondence principle. The improved agreement between quantum and classical behaviors as n increases is expected, because for large n the energy interval is small compared to the total energy, because whenever we are increasing the values of n, the interval between the energies they decreases. As such, the classical motion is approached wherein the energy is continuous. So when we are considering very high that is for large n, so what will happen actually for very large n, the spacing between the quantum states, that is they will approach very closely. So energy interval is small compared to the value of the total energy. So you have to focus on that, that is for large n, if we consider the energy interval is actually we can represent it in terms of h cut omega, because En is equal to n plus half into h cut omega. So interval between the energies, if you consider any interval, so that will be of the order of h cut omega. But if you increase the number value of the n, then what will happen, the value of the total energy will be very high compared to the value of the energy interval. We have to think this sentence in this way, that the value of the total energy is very high compared to the energy interval. So in that sense we can say that energy is almost continuous in nature, although in quantum mechanics we say energy values are discrete, because we have already deduced that En is equal to n plus half into h cut omega. So there from this equation we can say that values of the energy must be discrete. For different values of n we will obtain different energies. But when we are considering very large n, then we can say that value of the total energy is very compared to the energy interval. In that sense we can say that energy is almost continuous and it has approached to the classical limit. That is why this is in accordance with the Bohr's correspondence principle, which asserts that for large quantum numbers, quantum mechanics gives the same results as classical mechanics. So this is the discussion regarding the quantum harmonic oscillator, and for further understanding I request you to go through some standard textbooks. The content of these lectures are from the books of Aruldas and Eigen. So I request you to go through these textbooks for further understanding regarding the quantum harmonic oscillator, and I thank you all for listening the lecture.